Hi everyone, and thanks a lot for clicking on my talk. Today I'm gonna speak about explaining the PTA signal and dark matter with a conformal dark sector, so let's get started right away. We have two problems in cosmology, at least. So one is dark matter, which is that there needs to be 26% of dark matter compared to the total energy density in the universe in order to explain the structure of the CMB, galaxy clustering, the bullet cluster, you name it. And then on the other hand, in astrophysics, we have the problem that we observed now the PTA signal, which is great, 2 years ago, but we don't know where it comes from. There's the main hypothesis, which is that it comes from supermassive black hole binaries. However, those were again recently shown using n-body simulations to only account for a fraction of the total observed gravitational wave background. So naturally the question arises whether those two things, the source of the pulsar timing area signal and the origin of dark matter, if they could be related. And this is also the topic of my talk today. So now if we look into detail into the observed gravitational wave background, if we want to explain it by an early universe process, involving also eventually the freeze out of dark matter, such as a first order phase transition, giving mass to particles, we find that we need a very strong first order phase transition with an alpha value of above 1. We need slow transitions which happen over at least 1/10 of a Hubble time scale at that point in time, which is the 10 MeV temperature scale. However, there is no such first order phase transition in the standard model at 10 MeV, so quite naturally we are also led to a transition in a dark sector scenario, which also explains why so far we haven't seen such a Higgs boson responsible for such a transition at our collider experiments, just because it's so feebly coupled. Now, two questions arise, which are one, does precision cosmology allow for such a first order phase transition? And the second one is, does particle physics allow for such a first order phase transition? Now, concerning the first question, at those temperatures in the early universe, the formation of the early elements happens. This depends strongly on the expansion speed of the universe at that time, described by the Hubble rate. We can also alternatively quantify the expansion speed by n effective, the number of neutrino-like degrees of freedom, and you find both BBN and CMB much later during recombination to be consistent with 3 standard model neutrino species. So in order to not mess up with BBN and the CMB precision observables, we need to get rid of any kind of extra energy density. If we don't do that, we figured out in 2023, just when the data came out, that if you assume that the energy liberated in the dark sector stays there, if it's a completely secluded dark sector, you cannot explain the pulsar timing area data, just because delta n effective, due to this amount of released liberated amount of energy density, would be way too large, much above 0.22, which is the Planck allowed value. Now also at the same time, beta of h would need to be too low, meaning that the bubbles would need to be too large, much larger than what we can currently but much larger than the values of beta over h for which we can trust or simulations of the gravitational wave spectra. We found a way around, which is that we can still obtain a pretty good fit, better than supermassive black holes, to the pulsar timing area data if the dark sector decays before the onset of BBN. Now, what happened since then in the last 2 years is that people studied all kinds of dark sector scenarios, like specific models, which might explain the pulsar timing area signal. The minimalistic setup looks like this. You have a dark sector consisting of a dark Higgs and a dark gauge boson, which obtains its mass during this transition. Then you have 2 ways to couple it to the standard model. One is Higgs mixing, so the mixing of the dark Higgs boson to the standard model Higgs. The second one is kinetic mixing, which is the mixing of the dark A prime, the dark photon, with the standard model photon. However, the decay of the dark photon, the dark Higgs boson to electron pairs before BBN is suppressed by this kappa, the kinetic mixing parameter to the 4, because it's loop suppressed. So what we did in the work that I'm now presenting is that we avoided those difficulties on the theoretical side by introducing another particle in the dark sector, which is eventually also a dark matter candidate, and making the potential conformally invariant by basically crossing out the mass terms. So this then allows us to thermalize the dark sector in the standard model more easily, because this is only suppressed by kappa squared, not kappa to the 4 as previously. And quite naturally, we also obtain very strong gravitation wave signals. How do we do our analysis? So we performed a global fit, including all kinds of relevant likelihoods. First, from dark matter direct detection, from indirect detection, and from the bullet cluster, on top of the ones from BBN and the CMB, and obviously also from the pulsar timing array data. We found some region in parameter space, which explains 100% of the observed dark matter radiative density, as well as the pulsar timing array data, which now consists of some contribution from supermassive black hole binaries, as you can see by the blue line in the plot, plus some contribution from the first order phase transition. And what we also obtain is a testable prediction for beam dump experiments, because our dark photon would be visible in those. So let me come to my conclusion. In summary, PTAs can probe the pre-BBN universe, which is big news. We found that a dark sector phase transition can explain the pulsar timing array data better than if you assume it to be only due to supermassive black hole binaries. How did we do this? We performed a global fit, including all relevant likelihoods, and we found a best fit scenario, which can explain it, plus dark matter, and can be tested using future beam dump experiments like LDMX. Thanks a lot for your attention, and I'm looking very much forward to your questions.